In this video, we're going to learn how to solve a utility maximization problem when we have a perfect substitutes utility function. Mila loves both chocolate and vanilla ice cream and sees them as perfect substitutes. Her utility function is given by 2c plus v, where c represents chocolate ice cream and v represents vanilla ice cream. Mila has $12 to spend on ice cream each week. If chocolate ice cream costs $6 and vanilla ice cream costs $2, then what is Mila's optimal basket of ice cream? So what do we need to know to solve this utility maximizing question? We need to know the consumer's utility function, the prices of each relevant good, as well as the consumer's income. How are we going to solve this question? We cannot use the standard tangency condition because Mila's indifference curves are lines and budget constraints are lines. And so there's really only one scenario where they can be tangent to each other, and that may not be the solution. So we have to rely on a sort of more intuitive method. What we're going to do is we're going to compare the ratio of marginal utility to price for each good. And whichever one is bigger is the good we're going to consume exclusively. So we compare the marginal utility of chocolate ice cream over the price of chocolate ice cream to the marginal utility of vanilla ice cream over the price of vanilla ice cream. And if we observe that the marginal utility over the price for chocolate is greater than the marginal utility over the price for vanilla, we can conclude that it's cost effective from a sort of like utility per dollar spent standpoint to purchase only chocolate ice cream for Mila. And if that's the case, she's going to purchase only chocolate ice cream, then she's going to use all of her income to purchase that ice cream, and her consumption of chocolate ice cream will be income divided by the price of chocolate. So we'll be sitting at the intersection point of the budget line where we're crossing the v-axis where v is 0. If instead we observe that the marginal utility of chocolate over the price of chocolate is less than the marginal utility of vanilla over the price of vanilla, then we would say, hey, she's getting more utility per dollar spent on vanilla ice cream, so she should consume vanilla ice cream exclusively. So we would then conclude that consumption of chocolate ice cream is 0, and the consumption of vanilla ice cream is as much as she can afford, which is income divided by the price of vanilla. So far, we've sort of compared these two ratios of marginal utility over price. Whichever one is bigger is the good we consume exclusively. There's one more situation we have to consider, and that is what happens if the marginal utility of chocolate ice cream over the price of chocolate ice cream is exactly equal to the marginal utility of vanilla ice cream over the price of vanilla ice cream. If this is the case, then any basket on the budget line, C times PC plus V times PV equals I, will be optimal. Why? If we're observing that these two ratios of marginal utility to price equal each other, that actually is a really important implication. It means that the slope of the budget line is exactly equal to the slope of the indifference curve. And in that case, the indifference curve is literally laying on top of the budget line. It's everywhere tangent, which means that she's optimizing as long as she's choosing an affordable basket. So it's a very specific edge case where there's really infinite solutions. Let's solve this question now that we have a general idea of the approach we are going to take. So here's what we know: the utility function, the prices of the two types of ice cream, as well as the income of our consumer. We're trying to find the utility or optimal basket of ice cream. So we know we have to compute these ratios of marginal utility over price. So the first thing we should do is probably figure out what the marginal utility of chocolate ice cream is and the marginal utility of vanilla ice cream. So the marginal utility of chocolate ice cream is the partial derivative of the utility function with respect to C. That's going to be equal to 2. Similarly, the marginal utility of vanilla ice cream is the partial derivative of the utility function with respect to v, which is 1. These constant values for our marginal utilities are where the sort of unique solving mechanism of this problem comes from, right? If we were to just set up the tangency condition, we would get like 2 integers is equal to 2 other integers, and they may or may not equal each other. And that's why we can't rely on the tangency condition, because it's not holding any information about C and B in it specifically. Instead, it's just telling us the constant marginal utilities and the constant prices. So we have to think about it from a different perspective. So now we have these marginal utilities, we can compute the relevant ratios. The marginal utility of chocolate over the price of chocolate ice cream is equal to 2/6, or a third. And the marginal utility of vanilla ice cream over the price of vanilla ice cream is equal to 1/2, which is 1/2. So I have my two ratios, and now we're going to compare them. When I say compare them, I just mean I need to figure out which one of these is bigger. So I observe that a half is bigger than a third. So I'm going to say the following: the marginal utility of vanilla over the price of vanilla is greater than the marginal utility of chocolate over the price of chocolate. And I'm going to draw a conclusion that because of this, C is equal to 0 and V is equal to as much as she can afford. From our computation of our two ratios, we concluded that C is 0. To be really formal about solving for V, we can actually technically use the budget constraint to solve for V. You can do this in a variety of ways. So we sort of said in a previous slide that we can think of V as being income divided by the price of vanilla ice cream, which would be 12/2, which is 6. If you don't like this, you can actually write out the whole budget constraint. So 6 times C plus 2 times V equals 12. And then you could remind yourself that you know C is 0, sort of canceling this term out. And then you could, working from this budget constraint, divide both sides by 2 and find that B is equal to 6. Really, this formula that I wrote up here, V equals I over PV, is just like a shortened version of using the budget line directly. So we have solved our problem. We determined that Mila's optimal basket is to consume 0 units of chocolate ice cream and 6 units of vanilla ice cream.